thank you so much, Professor Robert Scherrer, for joining me. And those who don't know Professor Robert Scherrer, he is working at Vanderbilt University in the physics and astronomy department, and he's a leading cosmologist, and he has contributed to our understanding of dark matter, dark energy, Big Bang nucleosynthesis, and so many other cosmology topics. And I also had the opportunity to work with Professor Scherrer when I was an undergrad here, and we also published a paper on Big Bang nucleosynthesis. And I love Professor Scherrer, and today, like, this is an opportunity for me to ask some questions to him, and I'm really glad, like, I'm here with you.
Okay.
And thank you so much for this
You're
opportunity.
very welcome.
Yep. So I just want to like ask you the most basic starting question. What made you decide that you want to be a physicist?
Well, I was kind of unusual in the sense that I wanted to do this from when I was a little kid. So when I was young, I was very, very interested in science. And I wasn't sure what science I wanted to do, but I knew that I wanted to be a scientist when I was in second grade. And I just stuck with it for 30 years, and that's how it happened. But most people don't. Most people don't make their decisions at the age of 8.
And when you were in high school, did you do any? I guess like the experience in high school was like different than like what it is now. So like, did you do any specific thing during high school that made you like decide, okay, like I want to do like physics in college?
I just read a lot. I mean, there wasn't this sort of emphasis on doing research at a very young age didn't exist back then. But I read a lot of books and a lot of, of course, the internet didn't exist either. So I read a lot about science and about astronomy and physics, and I decided that was the most interesting thing.
And as far as I know, like you went to Princeton for your undergrad,
Right?
And you went to Cambridge.
Well, I went to Cambridge as a Marshall Scholar, and then I went and got my PhD at the University of Chicago.
Yep. So how were the good old days?
Well, Princeton was really fun. They really put a lot of emphasis on undergraduate teaching there. A lot of friends there, and I worked with Jim Peebles, who went on to win the Nobel Prize, and he was sort of the person who kind of helped invent cosmology back in the 1970s. So that was a fun experience. Now the department was not in the business of recruiting people. They sort of tolerated you if you were good enough. They didn't push you into physics the way we do today. But it was a good experience. I learned a lot, and it prepared me very well. Cambridge was a lot of fun. I got to do some research there on my own at the Institute of Astronomy. And then Chicago was graduate school, so that was not fun because graduate school is not supposed to be fun. But I accomplished a lot, and I had a great advisor, Mike Turner.
And like recently, you can do your PhD right after your undergrad, and
that was true back then too. I took some time out to go to Cambridge. That was unusual. That was not a normal thing to do.
Okay, and a bit like question more about James Peebles. How was your interaction with him? Mostly because like now he's so like renowned in the field.
Well, he's not any different now. In fact, I was at a conference last week up at Princeton, and he's 90 years old, and he gave a talk, and he has not changed in 40 years. He's just a regular guy. He's from the Great Plains of Canada, and he's a very humble, friendly person.
Nice. And how was your PhD experience?
Well, Mike Turner was a great advisor, and it was also a great time to be doing cosmology because Chicago had grown this group of people who were doing kind of the interaction between particle physics and cosmology, and it was one of the major centers for that. So they had a lot of faculty, they had a lot of postdocs, and my advisor was very good at working with me. You know, his style of research was to give me a problem and get back to him a month later when I had something to show him, and I actually preferred that because I didn't want to be micromanaged, and so we got along very well.
Yep. And what was your main topic of research during PhD?
I started out doing some nucleosynthesis and like particle physics in the early universe. So we wrote one of the earliest papers on decaying particles in the early universe, and we wrote a fundamental paper calculating the abundance of dark matter. And then he didn't want me to keep doing that for my thesis, so he actually had me move into cosmic strings, which were very exciting for a very short time. And they kind of disappeared, but it got me interested in the subject of large-scale structure and galaxy clustering, which I worked on for a while.
And for those who don't have any idea about dark matter and dark energy, how would you explain to them, like anyone who is not a physics expert?
Well, dark matter, in a very short term, dark matter is what holds galaxies together, and dark energy is what's driving them apart. So, if there wasn't any dark matter there, the galaxies would be spinning so fast that they'd fly apart. So, it kind of holds them in a circular orbit. But we also see that the galaxies are flying away from each other faster than they really ought to be. And so, there's something that's repelling them, some sort of repulsive gravity, and we call that dark energy.
And or like what is the reason like why dark matter and dark energy were introduced in like the concepts of like cosmology in the very first place?
Well, it's the dark matter actually goes back to a guy named Fritz Zwicky in the 1930s. He was looking at galaxy clusters, and he saw that the galaxies were moving too fast to be bound together in these clusters, and so he said, well, maybe there's some kind of dark matter. Now he published in German, so he used the German word for dark matter. So he's really the first person to talk about dark matter, and then his work kind of lay fallow and unexplored for about 40 years. And then a woman named Vera Rubin, mapped out the rotation of galaxies and saw the same thing, that these galaxies couldn't be held together. This was the 1970s. They couldn't be held together. They were rotating too fast. Dark energy is more recent. That was not something people expected. There were a couple of groups working around 1998 who both were measuring the expansion of the universe, and they were expecting to see a particular form for the expansion, and they saw something nobody expected, which was this accelerated expansion, and that was the beginning of dark energy.
That's so fascinating. Actually, like when I was in high school, I I got introduced to this idea of like dark matter, and I didn't understand that much of math, but it was so fascinating as a high schooler to get introduced to all these like fascinating topics.
Mm-hmm.
And I bet like most of the high schoolers also like know all these topics like dark matter, dark energy, and black holes, and like cool topics like special relativity and so on, and the reality of nature itself just like is so fascinating
Mm-hmm.
that they just get inclined to uh, physics and they want to do physics
Mm-hmm.
major. So how would you say like your your transition kind of changed from like getting fascinated about all these topics and doing the actual math and like the computation?
Well, that's a good question. It kind of was a parallel thing because as an undergraduate, at the beginning of undergraduate year, you don't get to do all the fun stuff. You have to do mechanics and electricity and magnetism, which you know about because I taught it to you. And the sort of basic physics is a sort of 400 years old subject, so it's built up on a very long train of ideas. And so I was learning that as an undergraduate while at the same time, reading about these other things, but having no idea how you could actually, do research. And then I did a senior thesis at Princeton with Jim Peebles, which wasn't very good. We didn't really come up with anything publishable, but it gave me the background to then do a real research project the following summer with a fellow named Rocky Kolb, who was at Los Alamos at the time and then later moved to Chicago. So Kolb and Turner are kind of identified with this particular phase of cosmology.
It seems like you met a lot of influential people in your life who were pioneers in physics and cosmology. Who would you say was the most personally your most influential physicist for you?
I would definitely, it has to be my PhD advisor, Michael Turner, because he got me started, got me ramped up in research, kind of connected me to the field in a big way. So he would be the most influential. I mean, the others who were influential were Rocky Kolb, who I did my first real research paper with, and Jim Peebles, who supervised my undergraduate research, even if it wasn't very good. And then there's another fellow that most people haven't heard of named Ed Turner, who taught a course at Princeton on cosmic evolution, and that really got me interested in cosmology as opposed to other areas of physics.
Wow, that's cool. And would you say that the nature of physics itself had changed the way you do research and like the way you approach problems in like last 30, 35 years in your career?
Well, a lot of the practical things have changed. So, when I started out, my first 3 papers were typed on a typewriter, which for your listeners out there, you press these keys, but it's not on a screen. Um, so that was difficult, and you'd have to, do a rough draft and then recopy it. And then I quickly switched over to computer usage after that. It was much harder to find things and to make sure you had a complete list of references because the internet didn't exist. And if I was looking at some of my earlier papers, and it wasn't uncommon to have a paper that had maybe 6 references at the end of it, as opposed to 60. The archive, the preprint archive, has changed everything. I mean, it's made it much easier to know what's out there, and you can do complete searches and make sure you don't miss anything. As far as the kind of actual act of doing research, computers are much easier to use than they used to be. They're much more powerful. But I think there's still a place for analytic calculations, and people have not entirely abandoned those in terms of understanding what's going on. And of course, we don't know what's going to happen with AI in the next 2 years.
Also, like there is a lot of transition with AI, and the way you can just, like make all the work so fast, and
Yeah.
you can use AI to create the literature itself,
Yeah.
and you can use a lot of codes from AI. So
Yes, I'm counting on AI to dig up all my obscure papers in the future from the internet, so they will be correctly referenced. Uh, I know, and it's starting out. I figure in about 2 years, mathematicians will be obsolete because they'll be able to just prove everything with AI. But then there'll be a golden age when physicists can use all this math to do their work, and then in a few more years, we'll be obsolete too. But hopefully, it won't be that soon.
so as someone who is like starting fresh like college and who wants to be a physics major,
Mhm.
how do you think they should prepare themselves for the age of AI, especially like if they want to be a physicist?
Well, I think it's what's going to happen is it'll become a tool, just like computers are a tool. It's just a much more high functioning tool. So I think getting practice with it, being familiar with how you can use it to solve problems, and then of course being cautious about what comes out at the other end because you never know when it's fabricating things. You have to, that problem hopefully will be cleared up. But I think that being able to use it as a tool will be extremely useful in the future.
Do you use any tools like
Not,
ChatGPT?
I not on purpose. I mean, Google will pop things up. I've played around with it. I'm waiting for it to get very good before I jump into it. It will generate code for you if you ask it to calculate, to do various problems. But I'm not using it right now in a deep way.
Now, steering up to like a different direction. I want to like focus this section for more like students who are really passionate about physics and who wants to like pursue their career in physics. What kind of suggestions you'd like to give them, and how can they prepare themselves, especially in their early age, with all the expectations? Obviously, there is like the expectation versus reality. Like the things you're
Mhm.
gonna do later on is gonna be way different than like what you expected when you like encountered all these like cool topics in physics that made you realize that like you want to do physics in your career. So for someone who is early on, like maybe who is like 21, how can they prepare themselves mentally, like to be out there and be a real physicist?
Well, I think obviously besides coursework and learning the subject very, very well, I think you need to be prepared. Now, of course, experimental physics is quite different from theoretical physics, but I would say, like all jobs, physics research involves a fair amount of drudgery punctuated by a few spectacular fun discoveries. So, if I have 3 good ideas a year, I'm thrilled. But, there are the moments when you have a breakthrough, when you suddenly understand something or when you suddenly see something no one has ever seen before. And that makes the rest of it all worthwhile.
I like when I started my career in physics, I started with like just cosmology, and I
Hmm.
also worked with you. And later on, like I kind of like steered up to a different direction in like
Yeah.
I found myself more inclined to like the quantum world.
Hmm.
And how flexible do you think students should be like in terms
Well,
of
I
like
think
changing?
they should be very flexible, especially at the undergraduate level. If you're a college student,
Mm,
that's really when you're learning what you like and what you're good at.
mm,
And you should be willing to switch fields entirely. I mean, you may discover that, you like chemistry better than physics, or you're better at chemistry than physics, or you're better at math. The whole point of college is to kind of get a feel for what interests you and what you like to do. And I think it's important to be flexible, to not like rigidly focus on one thing and say I'm going to do this or die. Instead, to say this is what I'm interested in, but I'm willing to look at other fields.
And in your last, it's been almost like 3 decades. You've been like in academia, I guess, right?
Yeah,
Like in last 3 decades, you have like met all sort of students,
yeah,
and you have seen them like succeed as a physicist,
yeah.
and then also like in other like careers as well. So what do you think makes a student special, and and what are the characteristics do you think like a researcher, like especially a physicist,
Hmm.
should possess to be successful?
Well, I would say three things really. One is just, technical ability, which is really the only thing we test at the undergraduate level. Can you do the problem set? Can you solve the math problem?
Mhm.
And that's important. I mean, without that, it's almost impossible to do any kind of physics. And then the other things that we don't really test very well at the undergraduate level are imagination and creativity. That you don't really need to succeed at the undergraduate level, but as you move up and get farther and farther along in physics research, it becomes more and more important. And then finally, just stick-to-itiveness, or the ability to work hard when you're not making progress, and to work hard when you'd rather watch a show or play a computer game. That again, that's we sort of see that at the undergraduate level, but that's very important. Diligence, I guess, is what I would call it.
Mhm. Following up on the imagination part, I've also like read some of your blogs and some of the papers you like posted on archive.
Hmm.
How important do you think is imagination for a physicist?
I think it's very important. Now, it depends, of course, on what kind of physics you go into. If you're, but I think regardless of what area, being creative and coming up with new ideas is especially important in theoretical physics, because there are many ideas out there, and that there's been a lot of if you go to the archive, almost anything you think of, someone has looked at some point. So being able to come up with new ideas on your own, which most is not really expected of students until after they get their PhD. But that, I think, is really crucial.
Mhm. And some of the blogs I read that you wrote were about like aliens, and like they were like there was a paper, archive paper I think I saw about like how dark matter can like harm or kill someone.
Yeah.
So when you write these blogs and papers, what kind of like what is the motivation for you to like write these things?
Well, because it amuses me. I think some of those are less important to the world of science. I don't expect it's unlikely anyone's going to be building a huge research effort off of dark matter killing people. Um, and I don't think you can build a career out of that. I mean, I write one of those papers every few years, but I think they're interesting. I think they're fun, and I think people who read them mostly think they're fun. Now, the journal referees don't like them. I've had many, I have to push those through. They're not your standard boring papers, but I've gotten most of them published.
Personally, what is your favorite topic in cosmology that you get like fascinated about?
Oh, I don't know. I think what I would really, the mystery I would like to live long enough to see resolved is the question of what makes the dark matter and what makes the dark energy, because those have been around for so long, and it's such a mystery. It's so interesting, and I would like to see the answer to both of those questions.
Have you tried yourself to like think about these topics?
Oh, sure, sure.
Yeah.
So I've written papers on models for dark matter
Mhm.
and models for dark energy. But as I said at this conference last week at Princeton, I said, there's only ever going to be one right model for dark matter and one right model for dark energy. And everybody else and all those 20,000 papers are going to be wrong. So, you better reconcile yourself to that fact.
What is your contribution to the understanding of dark energy through your like research?
Well, I've written some papers that basically looked at uh, trying to unify. There's a lot of models for dark energy out there, more than you can count on 100 fingers. And what I tried to do in a couple of my papers is to try to look at um, generic features of a lot of these models and show that a lot of them converge to very similar predictions for their behavior at late times. And I would say those are the most interesting papers I've written over the last couple decades, and the ones that have gotten the most attention.
If universe was a novel, how would you describe its first chapter and the last chapter?
Well, the first chapter we don't actually know because you can trace the evolution of the universe back to earlier and earlier and earlier times. And formally, the equations start off with a zero in the radius, and then it expands out of that. But we don't really have the physics tools to understand what happens in the very, very, very first, microseconds of the universe. And then we don't really know how the story is going to end because we haven't figured out exactly what the dark energy is, which is the dominant contribution. So I would describe it as a novel where the first chapter and the last chapter got ripped out of the book, and you got to figure out what's going on from the middle chapters.
And again, like question about like the starting of the universe.
Yeah.
What is your personal opinion about the starting of time?
Well, again, I don't think. I mean, I am a religious person, but I don't think you can. I don't think in cosmology we have a good understanding of the beginning of the universe. Again, because our understanding breaks down at high energies, which is what happened in the very, very early universe. The energies are very, very high, and you really need a quantum theory of gravity to understand what happens. When you're combining very high densities and very high energies, and that's the holy grail of physics. If you could come up with a quantum theory of gravity, unifying quantum theory and gravity, you'd earn about 10 Nobel Prizes. I mean, this is the ultimate achievement, and it's really defied a lot of the smartest minds in physics, going all the way back to Einstein.
There are some theories like string theories.
Mm-hmm.
What is your personal opinion about like these mathematical models?
Well, I'm not an expert on them, but I don't feel that they've really paid off yet. I mean, I don't think that we've gotten predictions from them that you can test, and I don't think they've given us any explanation of what the early universe was like. Now, that doesn't mean they won't in the future, but so far, I think we're still waiting.
My understanding of like how physics has developed over like last 2 centuries or 3 centuries is like there was like this huge exponential discovery phase where around like Einstein's
Yeah.
like a time like we discovered like a lot of things, and there
Mm-hmm.
was also like quantum mechanics,
Right.
and then the kind of research kind of like a little bit shifted towards more like all these extremely big experimental
Mm-hmm.
projects, and also like I feel that things are a little bit plateaued around like this
Yeah.
decade.
I think that's absolutely right. I mean, people look back on the golden age of physics, which was sort of the 1920s and 1930s, the development of relativity, and then the development of, especially of quantum mechanics. And I think it was Paul Dirac who said it was a time when second-rate physicists could do first-rate work
Mhm.
because there were so many opportunities. And I think we got all of the low-hanging fruit. And nowadays, part of the problem is just that the experiments you need to test physics at higher and higher and higher energies have gotten so expensive and so large that they've put a lot of things out of our reach. And the same thing applies to relativity. Now, with relativity, we're very lucky. We've been seeing over the last few years the detection of gravitational radiation and the imaging of black holes. And so there's been kind of a renaissance in relativity, I would say, over the last 10 to 15 years, because physics is ultimately data driven, and if there's no data, you really can't figure out what's going on. But I think technology. Some people think technology in general has plateaued. My grandmother was born the year they invented the airplane, and by the time she died, you were flying all over the world in jets. And when I was born, we had jets, and we still have the same jets. So there's a lot of technology that has reached a mature stage and isn't going anywhere.
And what do you think is physics going to look like for next decade and next century?
Well, the next decade, I think the AI is going to be a big influence, and I don't know how it's going to be an influence. I think the big discoveries are going to be again in the relativity sector and things like gravitational wave detection and better imaging of distant objects, and we're getting better data again on the dark energy. 100 years, I wouldn't care to speculate. I have no idea what that's going to look like.
My understanding is that like while it was the golden age of physics, everything was very much like limited to just pen and paper, and you have all these like fascinating
Mm-hmm.
ideas, and it was like very less experimental physics.
Well, I think there was. You didn't have computers.
Mhm.
I mean, they did have. They did have computers. They were banks and banks of human beings who would do calculations for you. So there was a. It was you couldn't do a lot of computational simulation. So people had to be smart about doing analytic stuff. But there was a lot of experiment going on. I mean, the whole growth in quantum mechanics was driven by better and better experiments at the atomic level.
Oh, that's fascinating. And like from the shift of that kind of era to like this era where everything is like very result oriented. You have to publish like a lot of papers, and the academia has kind of like steered towards the direction of just like more like a publishing factory.
Yeah.
Um, like, do you think there will be a change in the future in academia, like where people still want to like people still value um, more of those discoveries than just like a
Well,
paper?
we hope so. I mean, you don't people. Everyone bemoans a system in which you're simply encouraged to churn out one paper after another, but no one actually does anything about it. So I would hope that it would to some extent uh, go back to a system where you're trying to do a few good pieces of work a year instead of just churning out a lot of stuff for the sake of publishing stuff. And part of that, I mean, part of it is just the mechanical things we talked about. I mean, back when you had to type a paper and get some artist to do your figures, you couldn't write 10 papers a year because it was just physically impossible. Now it's so easy to just churn out at the computer tons and tons of stuff, and I've been guilty of this myself. So you know,
I guess everyone is the victim of the
of the internet. That's
yeah,
right.
modern day internet and the
That's
academia
right.
itself. How is your day-to-day life as a professor and as a physicist?
Well, it's when you're a professor, you have a lot of other responsibilities. So, teaching is a big deal, and that takes a fair amount of time. Although I've always enjoyed it, it's always been fun. And then there's the tedious administrative stuff, which varies from one person to another. I mean, I was department chair for 13 years, so I had a lot of that. And right now, I'm running our undergraduate program in the physics department at Vanderbilt, so I'm doing a lot more administrative stuff. But it varies. Some days I'll get a lot of work done in research, and some days I'll just be grading tests, and some days I'll just be, you know, doing admin work. Like right now is a good time of year because classes are over, and I'm catching up on the admin stuff that I should have done months ago.
I have some more questions about like the earlier thing we talked about, like your understanding of the universe and your faith in God.
Hmm.
So how do you like see these two things coming together?
So I'm Roman Catholic, and I actually I'm a board member of something called the Society of Catholic Scientists, which was started by Steve Barr, who's a very well-known particle theorist. He came up with the he and Nelson came up with the Barr-Nelson CP solution, which is a little different from the Axion solution. And so I don't I don't see a contradiction there. People kind of assume that scientists are all atheists, but my experience has been that they're all over the map, just like every other you know collection of human beings. I mean, Steven Weinberg was a notorious atheist. Georges Lemaitre, who really invented the Big Bang theory, was a Catholic priest. So I don't see an issue there. Now I do think it's a mistake to try to use science to prove your religious faith because which some people try to do with the Big Bang theory because science is always tentative. Science is everything we believe could be shown to be wrong next week. Now probably it won't be, but you never know.
Mm.
But it means I'm not that worried about what happened before the Big Bang, which some people are. I mean, there's a fair amount of research out there on what happened before the Big Bang, and I find that I don't think we have. It doesn't bother me, and I don't think we have the tools to explore it at this point.
Can you explain more about what you mean by some people try to explain the religion using science?
Oh well, some people will say to you, the Big Bang proves that God exists because God created the universe. But if you look at, for example, Catholic philosophers dating back 1,000 years, they didn't believe that there was necessarily an instant of creation that the universe had to expand from. They just said that, space and time were, the fact that anything exists at all is the reason for the existence of God, that, there should be really nothing. And nothing doesn't mean, this is, I think, where Lawrence Krauss went wrong when he was writing his screed. He claimed, well, we can show that the universe be born from nothing, but he didn't really mean nothing. What he meant was a quantum vacuum with fluctuating states in it, which is not nothing. It's something. So
Yeah.
you have to be very careful when you talk about these issues, because people use words to mean different things. They use the same words to mean different things.
So this nothing can be actually something, and nothing is nothing.
Nothing could be nothing. Well,
Nothing-
there's a
nothing could
famous
be nothing,
joke,
yeah.
which would you rather have, complete happiness in life or a sandwich? And the answer is the sandwich, because nothing is better than complete happiness in life, and a sandwich is better than nothing. So, like I said, you have to be careful how you use these terms, because they mean different things to different people. It's really it's misleading for scientists to say that a vacuum with 4 dimensions and quantum mechanics imposed on it is nothing, because it's not nothing. It's very much something.
Hmm.
It's just empty something.
There are so many cool discoveries in physics. What are your top 3 favorite discoveries in physics, and how do you rate
Oh, I
them?
don't know. I guess I have to put the discovery of the microwave background, since that launched the field that I've worked in for the last 30, 40 years. That would be the top discovery. And then probably, hard to say, the discovery of the nucleus of the atom, which gave us pretty much all of modern physics. So that would be a top discovery. And then I don't know what number 3 was. Number 3 probably hasn't been done yet. I have to wait and see.
Maybe it will be you,
It won't be me, but we'll see. Somebody will get it.
Professor, so you have 1 minute to describe a cool topic in physics that anyone can understand.
Okay, so I'm going to explain how dark matter works. So you have a galaxy, and you can measure how fast things are moving around the galaxy. So they're moving with some velocity v, and that gives you the force that you need to keep them moving in a circle. Now, if you're very far away from the galaxy, the gravitational force due to the galaxy goes down like the distance squared, and that means that the speed of these objects needs to decay as you get farther and farther away. But instead, what we see is that the speed of these objects stays the same, so there has to be some extra force holding them in a circle, and that extra force is due to extra matter, which we call dark matter.
Thank you so much.
All right.